Welcome to the 1411 Labflow workshop. Today we are investigating the experiment number 9 in Labflow for CHEM 1411, which is Visible Light and Spectra Lab. You might be asking yourselves, why are we studying visible light in chemistry? The answer is that light has many characteristics in common with electrons. One characteristic in common is the wave-particle duality of light. Some properties of light are best described by thinking of light as a wave, and some others are better described by thinking of light as a particle. Once we understand the dual behavior of light, we can turn to electrons to see how they display the same wave-particle duality. So the classical physics could not explain the stability of atoms, but the theory of quantum mechanics did. And today, quantum mechanics is the foundation of chemistry, explaining, for example, the periodic table, the behavior of the elements in chemical bonding. So before we explore the behavior of electrons in the atom, we need to understand a few ideas about light. So the objectives of today's experiment are: number one, to study the visible portion of the electromagnetic spectra. Number two, to recognize different light sources as continuous or discrete. Number three, to identify various wavelengths, lambda, from a fluorescent lamp spectrum, and recognize the energy and color of a short and long wavelength. Number four, we need to learn to identify the wavelength of peaks of colored solutions and the wavelengths where the absorbance is 0. And the last objective is to understand the relationship between the color that our eyes see and the energy absorbed by the colored solutions. So as we do each week, I will give you a quick overview of this week's experiment, then we will go over a learning check, and towards the end of the workshop, we will go over the report that you need to complete. So let's start with the introduction of this write-up. If we consider the wave nature of the light, in the introduction, it is describing that the sun is the source of all electromagnetic radiation, EMR, electromagnetic radiation. An electromagnetic radiation goes from radio waves that are up to a mile long to very small wavelengths of gamma rays that are smaller than the width of an atom. So light is electromagnetic radiation. It's a type of energy that is composed of oscillating electric and magnetic fields. And you know that in vacuum, these waves move at a constant speed of 3 times 10 raised to the 8th power meters per second. That is the speed of light in vacuum. That speed is fast enough actually to circle Earth in 1/7 of a second. This is just for your information. And an electromagnetic wave, like all waves, is characterized by its amplitude and its wavelength. So the amplitude is the vertical height of the crest and determine the intensity or brightness of the light. So here on the right, we have wavelength, and the distance here marked in red is the amplitude, is the vertical height of the crest, is the distance from the crest. The greater the amplitude, the greater the intensity and the brightness of the light. Then we said that another characteristic of the wave is the wavelength. What is the wavelength? The wavelength is the distance between two adjacent crests. So here they are writing the distance between two adjacent crests. It's marked in blue. It's longer for the top wave. The middle wave has a lower, a smaller wavelength, and the one at the bottom has the smallest wavelength. The wavelength, we use this Greek letter lambda to characterize, to identify wavelength. So when you see that letter, you will know that you are talking about wavelength. Like all waves, light is also characterized by its frequency. We use this letter for frequency. What is frequency? It's the number of cycles or wave crests that pass through a stationary point in a given period of time. Let me say it again. Frequency is the number of cycles that pass through a stationary point in a given period of time. If we look at the top, we have 3 different waves with increasing frequency. Look at the top, it has the longest lambda. But what is the frequency? Here is marked the same time, right? It says here is marked here in blue in a different color for the 3. So if we want to know which one has the lowest frequency, we have to count the number of cycles in a given period of time. If we look at the top, How many cycles? We can count the crests. We have 2 in this period of time. How many crests are in the second one? 1, 2, 3, 4. How many crests are in the lowest one? 1, 2, 3, 4, 5, 6. So which one has the highest frequency? The lowest one, because it has more cycles in a given period of time. And as you see, you can see this one has the highest frequency. The lowest one has the highest frequency and also has the lowest wavelength. So they are inversely proportional. One is higher, the other is lower. So in this graph, we see these different wavelengths with increasing frequency. For visible light, which is the light that we can see with our eyes, the wavelength determines the color. Let's look at the next. Depending on which wavelength we have, the color we are going to see. The white light, as produced by the sun or a light bulb, contains a spectrum of wavelengths and therefore a spectrum of colors: red, orange, yellow, green, blue, violet. And when you look at the visible spectrum, the red light here on this side has a wavelength of 7 or 750 nanometers and is the longest wavelength in the visible light. And the violet, when you look on the other side, has the shortest wavelength. The visible spectra goes from 400 to 700, or we can say 350 to 750. So violet has the shortest wavelength in visible light. So the presence of different wavelengths in white light is responsible for the colors we see. When a substance absorbs some colors and reflects others, it appears colored. For example, a red shirt appears red because it reflects mostly red light, while absorbing all the other colors. Our eyes see the reflected light. So the collection of colors make up the spectrum of the visible light, which is what we are seeing right here. The spectrum of the visible light. We can see here the electromagnetic spectrum with all the colors of the visible light. But remember, visible light only makes a tiny portion of the entire electromagnetic spectrum that we have here. It's only this tiny portion. we see wavelength in the entire portion of the electromagnetic spectrum ranging from here from 10 to the minus 15 meters on here, which are the gamma rays, all the way to the radio waves, long radio waves. And the lambda that is in this scale is about 10 raised to the 5th power in meters. So now we have an idea of what is the electromagnetic spectrum. And when we consider this is all the wave nature of the light, when we consider the particle nature of the light, we will learn that short wavelength light has a greater energy than the long wavelength light. And we will see, we'll learn in our practice what is the equation that Albert Einstein in 1905 proposed, that the light energy comes in packets, and we will use that equation. He proposed that the energy equals the constant, the Planck constant, times the frequency. We will go over in the practice test, and you will need in the practice problems, and you will need to use this equation to calculate the energy of the peaks at specific wavelengths in the report. And now here they are showing two different, a continuous spectra and a discrete spectra. In this part of the introduction, you need to know substances, particularly solids, emit a continuous spectra, where the intensity of light varies smoothly, as in A and C. Here, A and C will be this one. As you see, there are at each wavelength we have here a spectra, which is the intensity of the light versus the wavelength. And you see that at each wavelength we have a specific intensity. So that is called a continuous spectra. And the intensity of the light varies smoothly. But other substances, especially gases, emit a line spectra, which is a series of bands at specific wavelengths with no light intensity between those bands. So if we see this, only as these specific wavelengths, we see intensity of light, and 0 for the other wavelengths. So one of the things that you will have to do is to recognize different light sources as continuous or discrete. And the line spectra that we see here in D is more common in atomic gases, and the spectra is characteristic of each emitting element. So each element will have a different spectra, which is great because it will help us identify the element. So in part 1, you will analyze the spectra of different sources and determine if it's continuous or discrete. So the report consists of 3 parts. The part 1, just to analyze the spectra and determine if it's continuous or discrete. Part 2, we will look at a fluorescent light and will record the wavelength of the first 5 peaks. And then you will calculate the energy of those lines. And in the last part of the report, you will look at the spectra of colored solution, like a red dye, blue dye, green dye, and a yellow dye. And you will then record the wavelength of the peaks. And after that, you will be asked to conclude about the colors that your eyes perceive in relationship with the energy absorbed by the colored solutions. So this is the introduction that will help you answer the next questions. So let's do now. Let's share a page of some questions. Here you can see a spectrophotometer. What is a spectrophotometer? You will watch, there is a video in Labflow that you should watch and take notes of the details on how you have to clean, what do you need, the cuvettes, and all the elements that you need in order to use a spectrophotometer. But what is a spectrophotometer? It's an instrument that measures the intensity of light absorbed after it passes through a sample solution. So we talked about intensity, but now we need to measure. We are going to use that spectrophotometer. Spectrophotometers measure intensity as a function of light source lambda. So the spectrophotometer will give us the spectrum of a solution, which is the intensity of the light as a function of the light source wavelength, which is what we saw and we will see more. So we will have a graph of the absorbance versus the wavelength that is called spectrum. So here you see a diagram on how the spectrophotometer works. So basically, you have the white light, and then you have a prism, and you will decide that will separate all the different lambdas. And then you will pick one, in this case is the red one, the red color, and the light will pass through the sample. Then you have a detector and you will know how much of that specific wavelength the solution absorbs. So the spectrum, this is just a diagram so you can understand. So the solution here, we are going to use a cuvette. And we are going to place the cuvette inside the spectrophotometer in order to measure how much light the solution absorbs at a specific wavelength. The second question is, what is a blank solution? Well, it's a sample that contains everything except the analyte of interest. The blank is just the solvent. It's a sample of just the solvent. Why do we need a blank if we are measuring the absorbance of a red dye? Because the spectrophotometer needs to be calibrated against a blank solution. We use the measurements of the blank as a reference of absorbance 0. And then it will be related to the blank. So we calibrate, and the blank will be our absorbance 0. And the absorbance is the measurement of the ability of the substance to absorb light at a specified wavelength. What is the next question? If a photon has a wavelength of 431.2 nanometers, what is the energy of the photon in joule? This is, you will have to do that in part 2 of the report. You will have to calculate the energy of specific peaks. So let's practice here. You know, as I mentioned briefly recently, that Einstein in 1905 proposed that the energy the light energy must come in packets. And according to Einstein, the energy in a light packet depends on the frequency of the light. And he proposed this equation, that the energy equals the Planck constant, h, times the frequency. And you know that h is the Planck constant times the frequency, and the frequency equals the speed of light divided by lambda, the wavelength. So what is the value of the Planck constant? H is always, it's a constant, equals 6.626 times 10 to the minus 34 joules per second. 6 seconds. So this is the value of Planck's constant. And what is the speed of light? So we have this h. What is the value of the speed of light? The speed of light, we said that equals 3.00 times 10 raised to the 8th power meters per second. So we have the value of h, we have the value of the speed of light, and what is the value of lambda? They are telling me that is 431.2 nanometers. And because the units of the speed of light are in meters, and this is in nanometers, we need to use a conversion factor. So let me go down here and write E, the energy is going to be the Planck constant, which is 6.626 times 10 to the minus 34 joule per second, multiplied by the speed of light, which is 3 raised times 10 raised to the 8th power meters per second, divided by, because lambda is in the denominator, 4,312 nanometers, and we need to use the conversion factor. I will do it in a different color because we have very little space. And what is the conversion factor? 10 raised to the 9th nanometers per 1 meter. And then the units, the nanometers cancel with the nanometers, the meters cancel with the meters, and the seconds cancel with the seconds, and my units are going to be in joules. So when you do these calculations, you will find that the energy, when you multiply all that, is 4.61 times 10 raised to the minus 19 joule. Very good. So a packet of light is called a photon or a quantum of light. And this is how you are going to calculate the energy of a specific wavelength. And you are using the particle nature of the light. You are using Einstein equation to calculate that. Very good. Now, let's look at the last question. It says, let me erase here now, and we are going to look at this question number 4. It says, what is the color in the visible spectra with the highest energy? How do we know what is the highest energy? You know that the highest energy, because we had that formula, energy is the constant times this is the Einstein. So you know by this equation that if this number in the denominator, the wavelength, is smaller the energy is going to be higher. So the smaller the wavelength, the higher the energy. So if they are asking the highest energy, we have to look at the lowest wavelength. And violet is the color of the highest energy, with a wavelength right here between 380 and 450. If we look on the other side, red is the color of the lowest energy, and thus the highest wavelength in the visible spectrum. But what if I ask you, what is the color of the highest frequency? The highest frequency will be the highest energy, because this, remember, this energy is the Planck constant times the frequency. And also because frequency equals the speed of light divided by the wavelength, we know that a higher energy is a higher frequency. They go together. If we have a light of high energy, it will have high frequency. But the opposite is with the wavelength. And now we are going to share the page of the report that is pretty simple after you have listened to all my introduction. And I hope it will be clear and easy to solve. Okay. So as you see, the report has 3 parts. The first part is to recognize if the light is a continuous light or a discrete light. And for that, you will look at sample data. The second part is to calculate the wavelength of an overhead light spectrum. And then you will have to calculate the energy using the formula that I just showed you. And the last part is colored solutions. So in order to do that, let's look first at the sample data that you will have to look. So this is the sample data that you have to look at. For the part 1, right here, you will look at the source 1. Everybody knows this red LED light. And this is the emission spectrum. And what do you have to decide if it's continuous or if it's discrete. And we learn continuous is that a specific frequency, it has an intensity. And we saw at the beginning, when I gave you the introduction, we mentioned that gases are the ones that will give you a discrete spectrum. So looking at the sources, you see that mostly we mention that the white, you see intensity at almost, there is continuous light. We see all the colors in the white light. So we are going to conclude that the LED and the visible is continuous light. So this is the first part, and you will notice the difference. Look at this spectra. This spectra has intensity, is a continuous spectra. You cannot find a wavelength that you don't find the absorbance. You cannot see the light. So you will say that this is continuous. But look at the big difference of the helium spectrum. You will make your conclusions. What do we say about the gases? We said at the beginning that some substances, particularly solid, emit, the emission spectra is continuous. And we also said that some other substances, especially gases, give us an emission spectra that are narrow bands at just specific wavelengths. So if we see here, we see different bands, and we see no light intensity in this emission spectra between those bands. So this is clearly a discrete spectra. And we said that line spectra is more common in atomic gases. So this is the first part that you will have to do, looking at the data. This is all for part 1. You have different sources, and if you don't see a spectra like this, you will say it's a continuous spectra. Let's look at part 2. What do you have to do in part 2? They give you a fluorescent lamp spectra. This is a continuous spectra because there is always light intensity, and there is continuous. There is always absorbance, or emission. So what do you have to do in part 2? Basically, you have to calculate the energy of line 1, 2. It says, calculate the energy of line 1 using the wavelength you entered in table 1. So it seems that first you will have to, pick 1 in this spectra, pick 2, pick 3, pick 4, and pick 5. For these 5 picks, you will have to look. Here is the wavelength. So you know this is 400. Look carefully, and for me, let's say I wrote this is in nanometers, for the peak number 1, I wrote 406 nanometers. You will write approximately your number. So when you look at this scale, you will have to identify exactly this peak. Let's look at, let's say, peak number 5. When you use a ruler and you mark this wavelength, Well, I wrote 552 nanometers. So the first part in part 2 is to identify the first 5 peaks and identify the wavelengths of those peaks in this continuous spectrum. The second part is calculate the energy using the formula that I gave you. Let's say for number 1, just to do one, the energy for the peak number 1 is going to be the same as we did before. It's going to be the constant, the Planck constant times the speed of light divided by the wavelength. And for us, it will be 6.626 times 10 to the minus 34 joules per second multiplied by the speed of light meters per second divided by the wavelength, and we said we mark 406. So I will write here 406 nanometers. And then we need to use the conversion factor, that is 10 raised to the 9th nanometers divided by 1 meter. This is our conversion factor, so we can eliminate the nanometers and meters, and our units are going to be in joules. So I obtain for this, just this peak number 1, that my energy with this value of 406 nanometers for the first peak equals 4.90 times 10 to the minus 19 joules. And the same way you will have to do for the 5 peaks. And then for the part, so you will repeat this in part 2. And then in part 3, all you have to do is, these are absorbance spectrum of different dye colors. So here is the absorbance spectra of the red dye. If you look at, they give you the spectrum of the blue dye, they give you the spectra of the green dye, and they give you the spectra of the yellow dye. So the first thing that they will ask you is, let's look, what is the wavelength of the first peak in the spectrum from red solution? So let's go back to the red solution. That will be this one, red solution. We have a red dye, and they are asking, what is the wavelength of the first peak? You see the spectra here. This is the spectra. It has 2 peaks, right? You pick the first peak and you will identify the wavelength of the first peak. For me, I wrote 424. This is in nanometers. Then they ask you what is the wavelength of the second peak. So you do the same for the second peak and write the wavelength. And then they say what is the wavelength of the first peak in the spectrum of the blue solution. So this is the blue solution. And again, you go to the first peak and you identify the wavelength of that peak. And then they will ask you what is the wavelength of the second peak of the blue. So this is the second peak. You just identify this wavelength and write it down. And then they will ask you same thing for the green dye and yellow dye. So the second part is very easy. The yellow dye only has one peak. So they will ask you what is the wavelength of the peak in the spectrum of the yellow solution. When you look at the spectrum, you will see that you have only one peak. And they ask you, what is that wavelength? And then they will ask you, as the last part, let me see, this is the part 3, and to conclude this report, they will ask you, what can you conclude about the colors that your eyes can perceive and the energy absorbed by the color solutions? So we talk about a little bit in the introduction. We said that the color of the solution that we see is the point of the spectrum with absorbance 0. So this is the point in the spectrum that begins to be reflected by the solution. So using that information, you can say, for example, let's look at the red dye. Let's look at the red dye. There are two peaks, one here and one here. This is the red dye, and where is the 0 absorbance? The 0 absorbance, where the absorbance is 0, here we have 0 absorbance, is in the red part of the spectrum. So basically, more than 600. This part of the spectrum has 0 absorbance, and this is why we see red. This is the color that we can see. And then you will do the same for the rest, for the different dyes, and this will conclude this workshop this week, and I hope this is helpful. Thank you everybody for coming today.